Imagine traveling to the absolute ends of the Earth, all to test a single idea, an idea that could completely rewrite how we see the universe. Well, that's exactly what we're going to talk about today, the epic, unbelievable quest to prove Albert Einstein right.
So, what does it actually take? I mean, how do you even begin to test a theory so huge it claims to describe the very fabric of reality itself? As you're about to find out, it takes a whole lot more than just a brilliant idea. For the team at the center of our story, it meant a journey that is, frankly, almost unbelievable. We're talking 50,000 kilometers, by train, by steamship across an entire ocean, and, get this, by donkey cart across the Australian outback.
And here's the craziest part. All that travel, all that planning, all that risk, it was all for one single fleeting moment. A window of just over 5 minutes that would either change science forever or send them all home with absolutely nothing.
Okay, so before we join that team on some dusty trail in Australia, we've got to understand the revolutionary idea that sent them there in the first place. What exactly was this cosmic puzzle Einstein had come up with?
Yeah, this is the perfect way to picture the massive shift in thinking. For centuries, we basically thought the universe was like a fixed, rigid stage. You know, a solid floor where planets and stars just moved around. But Einstein came along and said, nope, it's more like a giant, stretchy, bouncy fabric. A huge object like the sun creates a deep curve in it, and that curve is what we feel as gravity.
And that is the absolute core of his general theory of relativity from 1915. Gravity isn't some invisible force pulling you down. It's just the shape of space-time itself being warped by mass. We're not being pulled, we're just rolling downhill along the curves.
And I love this because it shows you the human side of the science. The whole idea didn't start with some crazy equation. It started with a simple thought experiment. If you're falling, you don't feel your own weight. For that one moment, it's like gravity just disappeared. He realized gravity and acceleration were basically two sides of the same coin, and he called it the happiest thought of my life.
So, the theory is mind-bendingly elegant, right? But it created a huge problem. How on earth do you prove it? It's not like you can just look up and see the fabric of space-time bending around you. Or can you?
Well, this was the genius test. If the sun is making a huge dent in space-time, then light from a distant star passing nearby should have to follow that curve. Its path should look like it's bent. The problem? You can't see stars next to the sun. It's way too bright. Unless, of course, the moon moves in front and blocks it out perfectly during a total solar eclipse. And that is what kicks off our incredible adventure. A quest to a place many people thought was completely impossible, led by a team that had literally everything to prove.
So let's meet our main characters. From Canada, you've got Clarence Chant, an astronomer who is just thrilled to be part of this historic moment. And then, leading the American team, you had W. Campbell. Now, Campbell was the best in the world at this kind of observation. But here's the key. He was a massive skeptic. He wasn't trying to prove Einstein was right. He was trying to get the correct answer, even if it proved Einstein wrong.
And just try to wrap your head around this journey. For Chant, it starts in Toronto. He takes a train across an entire continent, gets on a ship to cross the whole Pacific Ocean, and then faces a final, brutal trek across a desert by donkey cart just to get to the spot. It's just monumental.
And their destination, a place called Wallow, was not exactly a five-star resort. In fact, a rival British team had looked at it and basically said it was impossible. It was on the edge of a desert, no roads, nothing. The coast had these insane high tides that made landing heavy equipment incredibly dangerous. It was the definition of the middle of nowhere.
So, after months of travel and weeks of painstakingly setting up all this delicate equipment in the brutal outback, everything, the theory, the journey, their careers, it all came down to just a few hundred seconds.
5 minutes and 15 seconds. That's it. That was the total time the sun would be blocked. That was their entire shot. Every single photograph, every measurement had to be perfect. There were no do-overs.
And of course, it almost all went wrong. At a critical moment, a cord they were using to change the photographic plates snapped. One of the guys later wrote, "We were horrified." Can you imagine the sheer panic? It looked like the entire thing was a failure. But they scrambled, they improvised, and they managed to get their pictures.
Okay, and here's where the story really turns. The eclipse is over. They have their precious glass photo plates. But now, the real work begins. And for our #1 skeptic, W. Campbell,
This was the moment of truth.
Back at the observatory, it was months of painstaking, tedious work. They had to carefully develop the plates and then use these incredibly powerful microscopes to measure the exact positions of these tiny little dots of starlight, comparing them against photos of the same stars taken months before. And when the results finally came in, they were undeniable. Just look at this. The old physics, Newton's physics, predicted zero bending. Einstein predicted this very specific tiny amount of bending. And Campbell's results from Australia, they lined up almost perfectly with Einstein.
And that's what made it so powerful. The fact that Campbell, the world-renowned skeptic, was the one who confirmed it made the proof irrefutable. He went on that trip ready to prove Einstein wrong, and his own meticulously gathered data proved Einstein was right. The proof was absolutely rock solid.
But here's the thing, proving that something massive like the sun can bend light was just one prediction. Einstein's theory hinted at something even more wild, something that would take another 100 years to find. The universe wasn't just curved, it could also create ripples. And this really shows the two big ideas perfectly. In 1922, they saw the evidence of space-time shape. But Einstein also predicted that when really catastrophic things happen, like two black holes smashing into each other, they send out ripples in space-time itself, gravitational waves. He basically predicted that one day we could literally hear the symphony of the cosmos.
So how do you hear that? With an incredible instrument called LIGO. It's genius, really. You take a laser and split it down two super long tunnels. The light bounces off perfect mirrors at the end. Now here's the magic. When a gravitational wave passes by, it literally stretches one tunnel and squeezes the other. That tiny, tiny change knocks the lasers out of sync, and that creates a signal, a little chirp. And in 2015, we finally heard it, the sound of two black holes colliding over 1 billion light-years from Earth.
So what this all means is that the confirmation back in 1922, it wasn't the end of the story. It was just the beginning. It gave us a completely new lens, a brand new way of looking at the entire universe.
That simple idea of bent light is now one of the most fundamental tools astronomers have. We use this principle called gravitational lensing for everything. We use it to take pictures of black holes, to find planets around other stars, and even to map the invisible dark matter that holds entire galaxies together.
And this part just blows my mind. The exact same physics that Campbell measured using our sun is what we now use on a cosmic scale. It's just a remarkable testament to the power of the idea. What works for our little star also works for giant structures millions of light years away.
So it all makes you wonder, right? The incredible journey to Walla let us hear the first note of Einstein's cosmic symphony. A century later, with gravitational waves, we finally heard another part of the melody. What else is out there? Just waiting for the next impossible journey in the next 5 minutes of truth.